Hi everyone, in this video we're going to continue on with the rest of section 2 of chapter 4. And so the first thing that we can talk about here, after last video we talked about the CDF a lot, and it's important to note the relationship between the PDF and the CDF, okay, because we sort of derive the CDF using the PDF. And in fact, we can obtain the PDF from a CDF. They have this relationship. And the relationship is that if x is a continuous random variable with a PDF lowercase f and a CDF uppercase f, then at every x at which the derivative x exists, then the derivative of the CDF is the PDF. Okay, so if I can take the derivative of the CDF and it exists at all places, so if the derivative exists where x exists, then we're sort of good, and the PDF is the derivative of the CDF. Okay, and so we found that the CDF in the last example, in the last video, that the CDF of a uniform distribution was the following. 0 if x is less than a. So if x has a uniform distribution on the interval a to b, then the CDF is 0 when x is less than a. It's x minus a over b minus a. Oh, I'm something on my iPad. Everything just goes away. It's infuriating. But we've got uniform a to b. We said before CDF is 0 when x is less than a, x minus a over b minus a when x is between a and b, and 1 when x is greater than b. Okay. Now, we don't really care about the 0 and 1 case, so I don't care about those too much. We'll put a line through it. I care about, or rather you could think, what's the derivative of a constant? And that's 0, so I don't care about either of them because they're going to be 0. They do still exist and they're there, but what I care about is that middle part. And so to take the derivative with respect to x of x minus a over b minus a, you have to think, what does that entail? Well, really I should split up this fraction into x over b minus a over b minus a. That might be helpful. Derivative of x is 1 times the constant that's along with x, and so that constant is 1 over b minus a. And lo and behold, that is the functional form of the PDF of the uniform distribution. The PDF of the uniform distribution, if you remember, is defined as 1 over b minus a when x is between a and b, and then 0 elsewhere. Oh. Okay, so sorry. Where are we at? We were. I'm so sorry. We are. It skipped. So we were here. Great. So there's the. There's the PDF from the CDF. Okay. Now, let's move on to the expected value of a random variable. So now we're moving on to moments of that random variable. Okay? And so if you'll remember way back to discrete land or discrete world, we found the expected value by taking the sum over all x of x times the PMF. And so what do we change? Well, we change the sum to an integral, and lo and behold, what have we found? That turns out it is just changing the sum to an integral. Okay, so I'm taking the integral over the entire support of the random variable. And so that was a fancy term that we hadn't used before, but wherever the random variable is defined, whatever are possible values of that random variable, it's called the support. Okay, and so we take the integral over the whole support, which could be negative infinity to infinity, of x times the PDF of x. Okay, so as always, let's try it out. So I have the distribution of the amount of gravel in tons sold by a supply company in a given week is a continuous random variable x with a PDF that looks like this. Okay? 3/2 times 1 minus x squared, where x is defined from 0 to 1, and it's 0 otherwise. So let's find the expected value of x. Well, the expected value of x is equal to the integral from negative infinity to infinity of x times f of x dx. So let's substitute things in. Well, it's only defined on the interval 0 to 1, so we know our bounds here are not negative infinity to infinity, they're actually 0 to 1. Okay, of x times the PDF of x. So that's 3/2 times 1 minus x squared dx. Okay, now what can happen? Well, the 3/2 can come out in front, right? It's a constant, so a constant moves out in front of an integral, and I'm left with the integral of x minus x cubed dx. Integral from 0 to 1. So if we move over here, we get 3/2 times, now if we take the antiderivative here, we get x squared over 2 minus x to the 4th over 4. And that is evaluated on the interval 0 to 1, or it's evaluated at 1 and at 0. Okay, and then you multiply by 3/2. So if we substitute a 1 in there, we get, well, I guess out in front it's still the 3/2, so we get 1/2 minus a 4th. That's the sort of first part. And then when we substitute 0 in, it doesn't matter what 0 sort of is. 0 squared is 0 divided by 2 is 0, and then 0 to the 4th power is 0 divided by 4 is 0. So the second half is really not so important because it's all 0. Oh, I did. I'm going to write everything down quickly here without all the extra stuff. It's really 0 to 1 of x times 3/2 1 minus x squared dx. Okay, the constant comes out in front. Integral from 0 to 1 of x minus x cubed dx. So it's really 3/2 times x squared over 2 minus x to the 4th over 4, evaluated from 0 to 1. When you evaluate it at 1, that's a 1/2 minus a 4th. When you evaluate it at 0, what you're left with is 0 minus 0 on that side. Okay, so what you really get, when we move up here, is 3/2 times a half minus a fourth. Half minus a fourth is a fourth. And so I get 3 halves times a fourth, which is 3/8. And of course you can change that into a decimal if you want. Okay, but you get 3 halves times a fourth is 3/8. And that's the expected value of x. Okay, so just a simple sort of integral problem there. Now I want you to take that and do it to the same situation that you had before, this dynamic load on a bridge, but now find the expected value. Okay. Now, you can pause and do that your turn, but I am going to move forward just to finish out the rest here. Of course, when you talk about expected value, you talk about a variance. And the same things happen, or the same things are present as in the discrete situation. So you define it the exact same way, except with integrals instead of sums. So we used to have a sum here. Now it's an integral, but nothing else has changed. Okay, and in fact, the shortcut to finding the variance has not changed as well. So let's use my example that we saw before to find the variance of x. Okay, so we know, we found earlier on in this video, that the mean, the expected value of x, was 3/8. Okay, so we want to find the variance, and I'm going to find the variance of x by finding the expected value of x x squared minus the expected value of x quantity squared. Okay, so really all I need to do is find the expected value of x squared, where it's x squared in the inside. So to do that, it's going to be the integral of x squared over the whole support, which turns out to be 0 to 1, of f of x, which is 3 halves x minus x squared. Sorry, 1 minus x squared. Dx. Constant comes out front. We multiply through, we get x squared minus x to the fourth. Oh, very rough time with that. Finding expected value of x squared, that's 0 to 1 of x squared times 3 halves 1 minus x quantity squared dx equals 3 halves times the integral from 0 to 1 of x squared minus x to the fourth dx. That's equal to 3 halves times x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1. Here I get, if I go up this way, I get 3 halves times a third minus a fifth. When I plug in 1, and then when I plug in 0, I still get 0 minus 0 again. So that second half really doesn't count. So I really have 3 halves times a third minus a fifth. Okay, and a third and a fifth, if we want to make fractions, it was probably easier to make it just a decimal here, but I don't have a calculator, so I'm going to do fractions. A third is 5/15, and a fifth is 3/15. So what you're left over with is 2/15. Okay, 5/15 minus 3/15 is 2/15. And when I do that multiplication, the 2's cancel out here, and I'm left with 3/15 or a fifth. So the expected value of x squared is a fifth, and we found before that the expected value of x is 3/8. So the variance by our little formula that is nice to use, it's going to be, it's the expected value of x squared minus the expected value of x quantity squared. So it is a fifth minus 3/8 squared. Okay, and I do not know what that is off the top of my head, but certainly plug that into a calculator and see what you get. But that's the variance. Okay, so again, our calculus work has sort of gone up. Okay, and also my screen keeps shutting off on me, so it took longer than it needed, but calculus work has gone up a little bit. But once we actually get into distributions and stuff, that calculus sort of requirement is going to go down. Okay, and so that's the end of section 4.2.